really happy to be among you here today. Thank you, first of all, Optimising for all the efforts you're doing for the community and for organizing these kind of meetups where we can see other people working in similar domain. So today I'm gonna hold this workshop called Optimization Schedules. Indeed, it's a hands-on guide to modern algorithms. My name is Amin Athmani. I'm a PhD in computer science and optimization, and I work at Dots and Lines, which is this AI company that is specialized in optimization and scheduling and routing algorithms in particular. I'm a senior consultant and senior algorithm developer there. So I worked a lot on scheduling algorithms, but also some routing. So we worked on airports, on ships, on schools, on scheduling also bigger enterprises, and that's where this presentation comes from. So I'm trying to. At the same time, I have a PhD, but I worked a lot in industry. My PhD was an industrial PhD. So I'm trying to always bridge this gap that Christina talked about, which is this gap between academia and industry. So for our agenda today, I'm gonna start by an introduction, a bit of timeline of scheduling, why it matters first and why it's hard. Then I'm gonna present the problem we are doing the workshop on. I chose the nurse rostering problem. Then I'm going to talk about MIP, how it works for this particular problem, and then a live demo of MIP. I already shared the code with you. And then we're going to talk about the alternative. If you are not doing MIP when you are solving schedules, metaheuristics are also a very good alternative, and I'm going to talk about that. And it happens that Timefold is a very good alternative to exact algorithms, and I'm going to present what Timefold is and why I think it's really interesting to be used in industrial use cases. Of course, this will be followed by a Codelab. So we will code together the models and solve this problem using Timefold. And we will finish by a deep dive into why Timefold is good for these use cases and some conclusions and takeaways from the workshop. So thank you very much for answering the question of the poll. I see that most of you heard about scheduling or worked with solvers in one way or another. I see some people working in metaheuristics. So that means that you already know a lot about these subjects. The goal of the workshop is not to teach you to model in MIP or to solve problems in MIP or Timefold or whatever. So the goal is to present to you some drawbacks that we are faced to when we are working in industrial use cases, and how do we do these trade-offs? How do we choose the best solver? How do we model constraints? How do we? So this is for you to know what exists, what's out there, and then it's up to you to choose what is the tool that you want to use. This is just sometimes it's maybe opinionated. I'm biased a lot by my experiences and everything. So please take all of this with a grain of salt. I'm not saying that any solver is the best. I'm not saying that any technique is the best. I'm just sharing what we notice when we use these tools in production and in industry. So first of all, scheduling is everywhere. I mean, we all know that scheduling is all around us. Wherever you go, you can find the use case of scheduling. And if you are working in the field, every time something happens to you in real life, you immediately start to model it in your head. What's this scheduling problem? What are the constraints? What's difficult about it? For example, if you go to the hospital, you will notice that nurses work a lot. They have these complex work schedules. They work nights. They have some skills that needs to be balanced. They have some laws. So you would find scheduling, for example, in hospitals. You find it in airlines and airports. So everything in the airport is heavily scheduled and heavily optimized. Warehouse workers also work shifts, and depending on the demand, depending on the skills, also they have some scheduling constraints. University timetabling is one of the most classical academic problems out there. So you have the high school timetabling, university timetabling. All of these are things that you would encounter in OR courses around the world. So this is also one of the use cases. Sports also is a very niche topic that interests me a lot, which is how to schedule all of these events of sports. And sometimes it's not just the big leagues, also the youth leagues, on the regional leagues and everything. That's where scheduling gets even more constrained, because you have one stadium shared between 20 teams or of all different ages, and that creates a lot of challenges with these types of events. We have also call center shifts, uh, one of the most annoying places to schedule, but it's also one use case that where you find scheduling. And the common thread between all of these is that what people are trying to do is they are trying to assign limited resources. We don't have infinite number of nurses, so we want to assign the limited number of nurses we have to the right time slots in order to have a functioning operations, and all by respecting the constraints. So we have a lot of constraints: legal constraints, physical constraints, well-being constraints that you have to respect when you are building your schedule. So with all of this diversity in terms of domains and fields and even constraints, comes a lot of complexity, both in terms of course, this is an NP hard problem, so it's a very hard problem to solve, and it's intractable and everything. But also, when you are modeling these constraints, you can come up with some really weird constraints, especially when you have a production schedule. And this is my next slide, which is why scheduling is hard. So first of all, because it's NP hard. So it's hard to come up with a good algorithm to solve it to optimality, or even solve it to some good enough extent. So even small instances have a very large search space, and the search space growth is sometimes exponential, and it can explode anywhere, anytime. So even for just smaller instances, you have a lot of possibilities that you cannot just go through one by one. Another extra level of difficulty is that the scheduling is all about time, and time creates this extra dimension that makes the schedules even harder. So what you do today can influence what you do tomorrow, next week, or even after 1 month. So, for example, you have this if you assign, for example, nurses, they have this legal amount of hours that they have to work, and they cannot exceed. And what you do on Monday can influence what you do on Friday. And if you couple that with some other constraints like skills and demand spikes and all of that, everything becomes even harder. And when it comes to applying this to industry, real world always brings some mess with it. So you have these preferences, for example, from people who are involved with these schedules. You have fairness, which is a very complex topic. Regulations that can sometimes change. So from 1 year to another, some laws can change, some union laws can come in, and even last minute changes, or one person getting sick, some demand that you didn't forecast right gets thrown into the mix, and this makes all the scheduling even harder. Here I just presented some brief history of solving schedules. So what are the techniques that were used to solve schedules throughout history? OR is is recent, but scheduling is not. So scheduling is, even when you are building a pyramid, you need schedules. And scheduling always existed, but the way to solve them didn't exist in the way we are doing it right now. Always, we have some old techniques, but the newer ones that deal with much complex
Yeah, I think we lost Amin, right? 'Cause I don't hear him anymore.
Yeah, I think we did last
Yeah.
him.
Okay, let's give him a minute. We can read the history. In the meantime. Oops. Amin, can you hear us?
Recorded.
I think
You are back.
stuff.
Yep, can hear you now.
Can you hear me now?
Yes. Welcome
Okay.
back. Don't go away anymore.
Was it this one?
Yes.
I stopped here or before this?
Yes.
Okay. So this one is just presenting some brief history of how we solve schedules. So in the 50s until the 70s, that was I call it the golden age of MIP, because linear programming was a hot topic. We had some branch unbound techniques. The simplex algorithm was also invented, and that made it the golden age of MIP, and that was also the roots of operations research. Then we had some AI thrown into the mix. So some early works of AI is constraints programming, but also we have metaheuristics and heuristics. In the early 2000s until now, we have more commercial solvers available for us. So what these have in common is that they have this model and run paradigm where you don't necessarily build the algorithm that solves your schedule, but you just describe it. So you describe it in a certain framework, and then these solvers will take the rest, will do the heavy lifting for you. And this trend of going to the model and run paradigm is what characterizes the last few years. We want, as developers, we really like these kind of solvers because you're not reinventing the wheel every time you solve a different problem. You just have to learn a framework and then apply that to your problem. So today's problem. So what we are gonna cover in this workshop is the nurse rostering problem. We're gonna do a very simple version of it because the complete nurse rostering problem is really complex, and I think we are doing just maybe 20% of the constraints. But these are the constraints that you would find in any nurse rostering problem. So the setting is the following. You are a hospital manager that needs to build schedules for your nurses over a planning horizon of maybe a few weeks, 6 weeks, 8 weeks. You have 3 shifts, morning, afternoon, night, that do not coincide. They are distinct shifts. And you have nurses with different qualifications. So some nurses can work in an ICU, nurses can work in a general setting. Every nurse has a different qualification portfolio. Some of them are unavailable sometimes because they are humans also. They need to take vacations. They are on a leave, sometimes on a sick leave. And they have some preferences for their shift types. Some prefer to work the afternoon, some prefer to work mornings. I'm not sure if there are some people who prefer to work nights, but maybe there are some people who prefer to do that. And your decision is to decide who works when. So you assign these nurses to the right shift slots throughout the days. So if we are talking OR language here, first of all, when you are modeling these kind of problems, one mental model that you can use is the hard constraints versus soft constraints. So you first start with defining the hard constraints. What are the non-negotiables? So these are constraints that if you break only one of them, your schedule is invalid because it breaks the law, it breaks a physical law. Sometimes if you assign a nurse into two places, that's not possible. And these are the hard constraints that you need to solve. The first one is the demand. So every day you have a certain demand with the required number of nurses per shift. So you have, for example, 3 nurses in the morning, 2 in the afternoon, and 1 in the night. That's a demand curve for you. 1 shift per day. So every nurse can only work once per day. It cannot work morning, afternoon, or afternoon more and night or something like that. Every nurse has to have at least 10 hours of rest between shifts. We can see how to model this one later. Some shifts need some qualifications, so you need to respect the qualifications of the shifts. So you match qualification between the shift and the nurse, and you need to respect their unavailability. So these are generally some vacations that you already pre-approved, so we don't want to assign shifts to them during those unavailabilities. But generally, you don't want to respect only the hard constraints, because if you only do that, you come up with a valid schedule that you will not be penalized by the law or something because you didn't respect the law. But people will be miserable and they will quit after 1 month or 2 months, especially with nurses and medical work in general. It's really stressful, and if you don't care about the well-being of the employees, they generally cannot stand it and they cannot handle the pressure. So you add all of these soft constraints that will make life better for these employees. For example, you want to give people, you try at least to give them as much of the shift they prefer as possible. So this is one of the constraints, is shift preference. And you don't want to give them streaks of nights. So if you don't want them to work 2 nights in a row, 3 nights in a row or more. So maybe that's acceptable in terms of law because you respect the rest gap. But when you do this to a person, his life will be miserable, and yeah, this is not good for long-term planning. So these soft constraints will define the quality of your schedule. So you want to respect all the hard constraints, and you want to respect as much as possible of your soft constraints. So let's do this in MIP first. What we are going to do throughout the workshop is we will do MIP first, see how MIP handles things and where sometimes it can fall behind, especially for industrial use cases. And then we will move on to Timefold and see how it's done with Timefold. So I think most of you heard of MIP. MIP is one of the most classical optimization approaches. And the reason why it got so famous is first because it has mathematical proof behind it. It uses the simplex algorithm, branch and bound, relaxation to LP, all of which are mathematically proven. But also because it was one of the first solvers or the first techniques that introduced this paradigm where you declare the problem. So you just describe the problem in equations, and then the solver behind the hood will do all the dirty work for you. So it will do all the branch and bound, and it will figure out the gaps and the relaxation and everything. So it offered people this general framework where you can solve pretty much any optimization problem. When respect, of course, you have to have linear constraints and everything, without actually developing the algorithms and everything. So it introduced this way of doing things, which is model and run. So you have to define your decision variables. In MIP, so mixed integer programming, you have continuous variables, but you can also have binary variables and also integer variables in your decision variables. Your constraints must be linear. This is one of the mostly noted the limitations of MIP because you have to linearize everything, and most of the constraints in real life are not linear. So this makes it a bit of a friction point when you want to use MIP. And of course, there are some techniques to linearize. There are some techniques to express things in a different way, like you've seen with the previous workshop from Jens, where you can play a bit with the model to make it faster, to make variables less, reduce the number of variables. But that requires most of the times great skill, maybe a lot of degrees. And yeah, this is one of the friction points of using MIP everywhere. And then you can also express an objective function. So the constraints here will define what we call hard constraints. And the objective function is what defines the soft constraints or the soft penalties. And you can minimize or maximize these penalties or objective. A lot of popular solvers exist. Some are open source, some are coming from academia. Also, a lot of these solvers are also not open source. They are paid. You have to pay a license for them. For example, IBM Cplex is one of the most known ones. Gurobi also is one of the most performant ones these last years. And Heist is a very, very good alternative. It's an open source. It has good enough performance. So this is a really good solver that you can use also. But what you can notice also in MIP is that the commercial solvers are dominating the space because they offer the best techniques, and they have a lot of techniques behind the hood to optimize the whole solver. They have heuristics, they have all sorts of techniques that they multi-threaded exploration that can make your MIP go a lot faster than the open source ones. But the open source ones are also good for some cases. So how would we model our problem? So this nurse rostering problem. So the way I chose to model it is the basic way of modeling, which is I define this XNSD. So it's three-dimensional variable, where N is the nurse, S is the shift. So we have three shift types: morning, afternoon, night, and D is the day. So basically, it's a binary variable that defines which nurse gets assigned to which shift in which day. So if we have, for example, x1 to 1 active, which means equal to 1, that means on day 1, slot 1, the first nurse is working that shift. And then based on this decision variable, we can define our constraints. So the constraints are the following. So the same h1 to 5 that we defined before. This one is the demand. So the sum over the nurses is the demand, and it's equal to the demand that's already defined. So this is something that the planner or the hospital manager will define. So you need this amount of shifts this day, afternoon, or something like that. So this is a simple one, the sum equal to the demand. You have this physical constraint, 1 shift per day. You sum over the shifts this time. For every nurse on every day, it has to be less than or equal to 1. So either 1 shift or 0 shifts. You cannot have more than that. The rest gap, what we did is we defined the forbidden transitions. We will see later what that means. It's in the next slide. And then in the qualification and availability, we just use something called variable fixing. We don't define the variable at all for those slots. So that means that nurse cannot be used on those slots. So XNSD equal to 0 on in those slides. So for the 10-hour rest gap, if you check the possible transitions from one shift to another, from one day to another, you will only find these possibilities. So either it's night to morning, night to afternoon, or night to night. And the only transitions that do not respect the 10-hour rest gap is these two first ones. So from night to morning and from night to afternoon. Those are the only forbidden ones. All the other transitions are allowed. And that's what we are doing here. So N here is the night, M is the morning. So from night to morning, you cannot do this transition. So this expresses it. And from night to afternoon, same thing. You cannot do that transition, and that's what expressed it. So this was the hard constraints. The soft constraints now, the first one expresses the preference penalty. So if
Yeah, I mean, we're losing you again.
Yeah, maybe this can be the precious time that people have a bit time to review the notebook, then life happens. This one is in for the first link that I sent.
Let's just wait a couple of moments for Amin.
He's nearly back. I saw him there. Just his video is not on yet.
Yeah, I guess as we're waiting, like Han mentioned, the Jupyter notebooks are already on chat. So if you want to go through it, some of the details that he mentioned in his slides are also on the notebook. So if you go through the notebook at this moment while we wait for Amin.
Siva, is there an option to pin a message in the chat of Zoom, do you think? Or
Sorry,
I will send it again. Is there an option to pin a message in the chat?
I don't think so. Do you
Okay.
mind sending it again if that's okay with you?
Yeah, for sure, for sure.
Thanks.
I see Stefan saying, can I ask a stupid question for smart OR people? Let's
Yeah,
see
go
if we have smart OR people here.
There's no
Okay, can you hear
question
me
that is
now?
stupid.
Yes, we can
okay.
hear you. Yeah.
Okay, I asked this question to Joffrey as well because I thought everything was linear programming, but he said no, we're doing meta-heuristics. But once I review the slide, I again see a lot of mathematics, and I fail to see the step going into, let's say, the columns and and let's say the linear programming part. Where do we do this, or do we never do this anymore? So I would expect something like a table with all kind of options, and then do a simplex to do the best solution. Or is this never happening for this kind of methods?
Hello?
Okay. Yeah.
I mean,
Jeffrey was asking, what do you mean? Also for me was not very clear, but maybe you can repeat that now that Amin is back. I mean, we were waiting for you, and then Stefan had a very good question. So
Yeah, Zoom keeps crashing. I'm using the app now. I hope things gets better.
okay.
Okay.
So my question was, I see a lot of mathematics here in a mathematical notation, but I would something like I would like expect to see something like a tableau with columns and rows, and be able to do a manual simplex operation on this. Does this ever happen, let's say, on paper, or is this always abstracted and never seen again?
What do you mean? So the
So
first
for example, you did your hard constraints. Will I ever see a column with this hard constraint in it?
a column.
No, what I think what he means is like, yeah, the idea is that you have this mathematical expressions, and then you kind of send it to the solver. But before sending it to the solver, there is this step of creating the matrix. That's what you mean, right? With the
Exactly.
columns. Yeah, exactly. But you don't see that in the sense that you can open the file and see it. So there is a file which contains the matrix, but you as a programmer, you just write the equations, and depending on what tool you are using, it's doing this in the background. It's like the pre-building the model. And then that model is sent to the solver, to the, let's say, Kurobi, if we talk about MIPS, right? So yeah, that's the answer.
So the matrix is always, in this case, abstracted, not seen from the programmer perspective. They only use for example, Pyomo to describe the problem, but never to do the old style things on paper. That will never happen. You will never define a matrix yourself.
No,
No.
but you can see it, and then you sometimes use it for debugging, because sometimes you have issues and maybe you go into the matrix to see what's happening. But usually now the debugging tool help you kind of navigate through the matrix as well without seeing it as a matrix. Like it just sends you to the row with a problem or the column with a problem, and then you start to debugging. Right.
Okay, thanks.
Yeah. So first of all, when you try to model things, you usually start with a pen and paper for MIP especially. So you write your equations, you try to linearize some if they are not linear, and then you have this languages that you can use to express these constraints in the language that the solver understands. So we will see that in the MIP notebook. And then the solver does pretty much all the rest. So it uses all the techniques to solve your equations. So I think I was in S2. S2 is the consecutive nights constraint. So what you would do here is it's an extra variable that detects when there's a consecutive night, and we try to minimize those consecutive nights. So that's also included in the objective function. So from what you see here, up until now, everything is clean. We have clean constraints, clean objective function. So this is where MIP shines usually. So I'm just have a demo here to share with you. So let me just move on to the demo. Okay, you should see this.
Yep, we see your notebook.
Can you see my screen, Siva, or
Yep.
the notebook?
We can see your notebook.
Okay, perfect. So in this demo, I already shared with you, it's in Colab, and you can run it. What we are doing is we are implementing these abstract equations right here. We call this mixed integer program. So we implemented you in using an open source solver, which is HEIS. And we are using also Pyomo. So Pyomo is a library that allows you to write, because we have multiple solvers that can run your MIP. And before Pyomo, we used to write one model per solver. So you have to write the model for Cplex, one for Gurobi, one for FICO, one for whatever solver you're using. But Pyomo made this simpler, so you write your model once, and then you can change what solver is solving this. So you can use, for HEIS is the solver, but you can also use Cplex or Gurobi or whatever you want to solve this model. And here we are using the HEIS solver because it's open source. So this is just I'm explaining the same thing I explained in the slides. This is defining the problem. So we have this nurse roster that contains the list of nurses, the demand, and the shift qualifications. Instance generation is something to generate a random instance, random of a different size. So I'm generating some instances here from small to extra large. So smaller ones have 10 nurses and 7 days. The bigger one has 300 nurses, 120 days. So you can imagine this is maybe a very big hospital with 300 nurses, and they plan usually over a big horizon. So these are some stats of the instances. We have the number of days, the demand. So utilization is how many slots need to be filled compared to how many slots are available theoretically for the nurses. So we have here 56%, and some special shifts, so pediatric shifts, ICU, and nurses with those qualifications. We have here a function that can visualize the schedule in a nice way. We will see it. And this is the whole formulation. So this is what you write with the pen and paper. And then this build model function will build the model using Pyomo. So if you can see here, we define the model, we define the different sets. So the set of nurses, set of days, set of shifts. And then we define our decision variables. So this big matrix, the X matrix. And then we can start by, so this one, H4, H5, even before adding all the constraints, I can already fix some variables to 0 because the nurse is either not available or not qualified to work that shift. So that's something we do. And then we add the different constraints. I will not go into details about how the syntax and everything, but it's the same model we used before. These functions will help me to check the number of variables and number of constraints in a model compared to the instance size, and then to solve it and report penalties if we find any. So let's start by solving the small instances. So small instances with 10 nurses and 7 days has 210 variables, 39 of which are fixed. So the nurses are either unavailable or unqualified. And what's left to be fixed is 170. And you can see here also the number of constraints. Let's try to solve that. MIP does really good. So in 0.08 seconds, it solves this to optimality. So there's no better solution than this. And this is one advantage of MIP is that it has a mathematical proof that you cannot find a better solution than this. And we call this the lower bound. And the gap is what's between your lower bound and your objective that you found. When that's 0, that means you found optimality. And let's visualize it here. You see in the left, you have the nurses. In here, it's the days. And then you have morning, afternoon, and nights, depending on the colors of the shifts. So what you can notice is when it's small and when the model is clean, MIP is really, really good. So under 0.08 seconds, it found already the optimal solution. But let's try to push this a bit further to the limit and make it real world, have some real world scenarios that we can have. So one scenario that can happen when you want to publish this to production or where you want to push this over to production is that sometimes the user will try to push it to the limit. So you know that nurses are not available a lot. Recruiting a nurse is expensive, and sometimes you cannot find the right nurses with the right qualifications. So they have some some instances or some schedules where the demand is just inflated. So the schedule is over constrained. You cannot solve the schedule. So if you give it to MIP, let's see what happens. So I'm trying to simulate this. So what I've done, I inflated the demand. So I multiplied, for example, with 1.5, so 50% more demand coming in. So that means that I don't have enough nurses to cover this. So the original utilization was 56%, now it's 76%. And let's see what happens when I do this with MIP. So when I solve this with MIP, so very quickly again, 0.03 seconds, it says no solution found. But imagine you are a hospital manager and you bought this expensive software that has all of this math behind the hood and solvers and everything. But then one day, in a Monday or something, and people expect their schedules, and you tell them it's infeasible. I cannot do anything for you. So this is simply not acceptable for something that is going to be pushed to production. And the reason why is that MIP by default assumes that you assume that the hard constraints can always be respected. And so when something unexpected happen and just one constraint doesn't get respected, sometimes it's not because the schedule is over constrained, but sometimes it's just the user entered something wrong. So imagine the user entered something wrong with qualifications. So one nurse should have the pediatric qualification, but they forgot to assign that skill to her, or one new nurse came in and we didn't input all of her credentials and everything. That can break your model. And that's just not acceptable in real life. Of course, there are some techniques in MIP that you can use. That, for example, this IIS, it's called irreducible inconsistent subsystem, that can be used. And Gurobi, for example, has it. Cplex has it. But that's also so expensive. And if you have a big instance, sometimes it's even not possible to compute that subsystem. And this subset of constraints, basically what this does is it tells you what are the smallest subsystem of constraints that poses a problem. So it will give you maybe 2 or 3 constraints that says just these 3 constraints are not possible to satisfy together. And that can hint you towards determine what is the issue of my instance. Yes, Zivo.
I mean, we have a question in chat.
Let me check.
So we have a question from Sohail who asks, so he first asked a question, but then he clarified the question at the end. And he says, the way we import the data into the model, does it affect the overall speed of solving the model itself?
Check. Yeah, so you can solve this by maximizing this is one way of doing things. So you allow for some shifts to be unassigned. This is also one way of doing this, but that means you change the whole formulation of your MIP. So you will need to push. So you will need to push some of the hard constraints into the soft constraint level, and maybe use some Lagrangian relaxation or something like that. But that changes your whole modeling technique. And even by then, whatever you leave in the hard constraints can block your model and can make some instances infeasible. And when something is infeasible with MIP, that's when you notice that it has no answer for your questions. And this is one thing I wanted to show with MIP.
So I mean, we had another question regarding like, does the way we do, based on the way we import the data, does it affect the speed of solving the model?
The way to import the data into the model affect the solve.
Does it actually affect the speed how to
No.
solve
So once it's built, once the model is built and the solver has everything loaded into memory, it's up to the solver to do that. And the build time is usually something neglected when compared to the solve time. But that's when we are talking about some manageable in size instances. So if you have very big instances, you have a lot of, for example, in this extra large instance, you will see how many variables we have. When you have a lot of variables, in that sense, even the build time is something that you need to consider because you have a huge matrix that you need to build. But also sometimes it's also a question of memory. When you have this huge matrix that you need to build, sometimes it just doesn't fit in the memory because you have millions of variables, for example. So that's something also that we stumbled upon before. You just don't have enough memory to put all your variables because the model is so big that you cannot fit it into. And that's sometimes you can fix those with changing the modeling, but other times, especially when you have to model the time in a more discrete, continuous way. So here we split the day into just 3 shifts. But imagine if we have more continuous time representation. So if you are representing, for example, every 15 minutes, a smaller granularity of representation, that means your model will explode because of this. Instead of having 3 variables, 3 shifts, you will have, for example, 1,000 per day, 1,000 slots per day. And that can also make your model so much bigger.
Yeah, that's a very good point. As you increase the complexity, that actually also increases the build time, and also like it will also like exceed the amount of memory that you would have in your computer as well. So yeah.
Yeah, exactly. Yeah. I'm not gonna deep dive into the MIP solver. I'm just trying to show some use cases where MIPs are frowned upon in industry. So just to have enough time to also show what Timefold can do. So again, this is what happens when you have an infeasible thing, and this is a very simple use case that I did just to showcase what would happen if you have an infeasible. But in generally in industrial use cases, you have 5 times more constraints, and if something is infeasible, you do not know where this infeasibility comes from. Is it a data problem? Is it a constraints problem? Is it a size problem? And this is something that MIP, the way we are doing it like this, cannot respond. And here we are, I'm not gonna run this, but I already ran it, scaling the base model. So I'm running it with small, medium, large, extra large, and extra large instances. And you can see we always find the optimal solution very quick. Maximum is 20 seconds. And this is, like I said, this is the clean model with some tight bounds. And this is where MIP shines because it can prove optimality, it can find optimality really quick. And this is usually a typical case where you would want to use MIP. But another thing that can happen in real life is that the client calls you one day or just send you a Slack message saying, hey, I have a new constraint. My nurses are complaining. So if you go here to this schedule, you can see nurse 4. She or he only has night shifts. This is not normal. So one nurse doing 4 night shifts, 3 night shifts, and one nurse doing nothing. So nurses are complaining. A lot of them are working a lot of night shifts all by themselves. So let's do something about it. Let's have this fair night distribution. This is a completely fair constraint to ask for because you need fairness between your employees. Let's try to express this using MIP. If you want this, one simple way to do it is this mean average deviation of mean absolute deviation of between what your nurse did and what the average is. So you compute the average of nights every nurse should do, and then you try to minimize the absolute deviation between what your nurse did and what the average should be. So that means that you do not want less than the average, and you do not want more than the average as well. So this is a very simple way to tackle fairness. Fairness is a complex subject. Sometimes you need a more complex thing to express it. But if you just do it with this very simple formulation, you would need to first linearize the absolute value, because it's not linear. The absolute value is a function that is not linear. And so to do so, you have to split it. Here we split it deviation over and deviation under. And that's the new penalty that you add. So let's do that. This is what this function does. So just a note, this mean absolute deviation is not the best way to express fairness. So even the simplest way required us to add new variables, so 2 new variables, and add a new. So these variables are linked to some other variables, and this will first of all make your model more complex, because the number of variables, just not just the number in total, but the number of types of variables explodes. Every time you add a new constraint, you have to add some new types to your model. So this is one, a complexity of your model. This is something that the developer will suffer from. But also, when you have these kind of expressions, especially when you try to linearize things and everything, you hurt the performance of your solver, because you make it more loose, and so you don't have the tighter bounds that you had before. So and that's even without expressing so for example, this fairness, you should do it with the variance, and the variance is not linear. That's why we couldn't use it with MIP. Yeah, this is something that's painful also. Next week, the client called again. We noticed that if you go back to the schedules, some people are doing just one type of shifts. So this person, for example, is doing just the mornings, this one just the afternoons, etc. So what we want is some diversity in terms of what shifts they are doing. And the constraint they want to express is no more than 50%. So no nurse should work the same shift type more than 50% of their assignments. And in order to express this second constraint, you need 3 new types of variables, and all of these types are linked together with the matrix that we had before, so the X and SD. And this makes your model even more loose, and you will lose a lot of the tighter bounds that you needed before. I will leave you the details, so all of this is in the notebook. You can read all of it. And then let's see what happens when you add these constraints and add all of these variables. So we have here the table. So the small is the base model that we had. Like I said, it's the clean model that works fine. And then S3 is the fairness constraints. S3 and S4 is the fairness plus the distribution of shifts. So if you see right here, in the large, for example, I set the time limit to 300 seconds, or 5 minutes. In the large, we just got it to optimality in 300 seconds. And then extra large and extra large, you hit the max time limit and you don't even get a feasible solution, not even a feasible one. We are not talking about optimality here. And if you notice, this S3 and S4, it's just soft constraints. What I would expect is that we said that you want to have a valid schedule first and then improve the soft constraints. But here, by adding soft constraints, I'm hurting even the hard constraints. I'm not even solving the hard constraints anymore because of the soft constraints. So because there's not this lexicographical order between constraints, even adding soft constraints can impact the performance of your hard constraint solving. And this is one other issue of MIP. Let me just go back to the slides just to show you what I'm talking about. So this is like I said, the fairness. In order to really express it well, you need variance, and variance is quadratic, so you cannot use it with MIP because everything needs to be linearized. This cross-training variety constraint needed 3 new variable families that couple variables all over the place. LP relaxation weakens, so solve times explode. And these are the results. So what we can have as takeaways from the MIP is that MIP work very well when you have small to medium scale in terms of size, but also in terms of nature of constraints and number of constraints. It's not about just the number of constraints, but also the nature. So when the constraints are non-linear and they are coupled to each other a lot, and this is really important with scheduling because what happens this week will impact maybe what happens next week and even next month. In reality or in industry, we have some constraints that span over 6 months in some cases. And this coupling between data and between constraints will make your model explode and will make your model suffer the performance cost. Yeah, so some constraints cannot be expressed naturally. So you see in word S3, we made some compromise. We linearized the constraint, but even then, we made the model a bit complex because we needed more variables. Complexity kills scalability. So this is whenever you have this loosen relaxation in the model, you have less performance. So when you have no priority between constraints, like I said, even the soft constraints can impact your hard constraints. So what you would want in practice is a solver that is able to first solve the hard constraints, at least solve that, so that the schedule is usable, because the schedule with at least one hard constraint violation is not usable at all. So you would want a solver that is at least usable, and then let's talk about the soft constraint. If you can do it, that's very good. If you cannot, at least you have a valid schedule in your hand. I mean, nurses will complain, but you did your job. You provided a valid schedule. Memory footprint is also something, like I said, to be mindful of, because large models sometimes do not even fit in RAM. And this is when you talk just with single-threaded solving, because all of these fancy solvers, they also have multi-threaded, and they can duplicate the model, and they can explore the tree in parallel. And parallelization comes with a bigger memory footprint. So if you cannot fit your initial model, sometimes even if you can, when you try to parallelize it, it will not fit your RAM. And with RAM prices, you don't want this to explode. When something is infeasible, usually it's a dead end, because MIP does not offer by default this least bad schedule. So it will never break hard constraints. And that's something that is by design. But this one is not acceptable in most cases in industry. And you notice this pattern of the client just called. It's really painful because sometimes you have to add variables, sometimes you have to make changes to your model. You have to linearize, and this happens all the time. So in reality, every week, every sprint, you have new constraints, new changes. When the board changes, they have new objectives, so you have to change the objective. And this is something that you need to be mindful of. Your model is not something that you write in paper. It's elegant. It has all of these tight bounds. Your model is something that will be served to people and that will be used and changed a lot and explained. So you have to be mindful of this. You don't want to build just something that works for just one use case and that's it. So you want something that is more general. I think we reached the break time. Let's take a quick break. Maybe if we have questions.
Yeah, we do have two questions on chat.
Yeah.
The first question is, how do we make sure solver prioritizes hard constraints over soft constraints?
So the MIP always prioritizes hard constraints. It's not a problem of priorities. It's a matter of MIP does not even give you the solutions that doesn't respect hard constraints. So it doesn't return them at all. But MIP always, when it says feasible, that means it satisfied all the hard constraints. But it doesn't have, we call this the anytime behavior. So some solvers have an anytime behavior where anytime you query the solver to get the solution, they will give you some solution. Sometimes it's not a complete one. Sometimes it even doesn't respect all the hard constraints, but it gives you something. And that's not something that is a feature of MIP. And we will see later that it is a feature of Timefold.
The next question that we got from chat is, which is quite interesting. Can we imagine a graph formulation of the form and use graph structure properties to model such constraints? That would also help if we have pre-established patterns of shifts.
Yeah, this is something that Jens covered in the previous workshop. You can model this as a flow problem, and by doing so, you avoid a bit the representation of time, because the representation of time is the most complex thing when you model scheduling problems. So depending on how you model time, all your model changes. Do you model time as a discrete thing, or do you model time as a decision in itself? So sometimes you can even model the decision of when does the shift start and when does it end. For example, in constraints programming, we do that. And that changes your whole model. But yeah, there are some tricks to change the formulation of MIP. I'm not saying that this is the best MIP that we can do. I just chose this MIP to show the limitations of MIP. And this is the most classical MIP that people would come up with. So if you don't spend a lot of time into this problem, you would come up with this formulation. And this formulation has these limitations. But the other formulation also have some of the limitations I talked about, like the infeasibility and like the explosion when you add new constraints. And so if you model this as a flow, sometimes the client will just come in and ask you to add a constraint that you cannot just do with a flow. So if people, for example, prefer prefer certain slots in the day, that's something that you cannot express naturally inside the flow formulation, for example. So even with changing the formulation, you will hit some of these issues I'm talking about.
Yeah, and the next question that we got is, apart from setting priorities for hard and soft constraints, is there any other cases that we need to consider priority?
Yeah, so even inside the soft constraints themselves, you need to consider to set up some kind of priority. So between hard and soft, you always have the lexicographical order. So that means that any hard violation, even by one, is worse than a violation of 1 million of the soft constraint. By definition, that's how the priority is. But inside the soft level, you also have some constraints that are more important than others. For example, if my hospital manager says that my S3, which is the fairness of night shifts, is more important than this variety, I would give more weight to this S3. So that's how you would express that priority. I think we have time for one more question. What do you think about Gen AI-enabled MIP formulations, either to suggest base functions? Yeah, I think that's a really interesting field that I think Optimization for All have have a conference about it coming in, maybe this Friday even, with some, I think you invite someone to talk about this subject. But I think Gen AI or LLMs can be really helpful when modeling. Just be careful because sometimes of course, they hallucinate and they can do nonsense. But I think this mixture of having the LLMs using OR techniques will be something that will work in the long run, either with MIP or with other techniques. So I don't think LLMs will be able to solve problems directly as good as these solvers, but the general framework that people are using lately is that the LLM will generate the model for you, and then the solver will take that model and run it. Because the LLM can never be as efficient as MIPS or metaheuristics in exploring the search space and everything, because they don't understand what the search space is. But this framework where you model using LLMs and then solve with a solver is really interesting. I think we will hear a lot about it in the future.
Yeah, what you say is true. I mean, so we have a Community Connect event that's happening on Friday that's going to talk about this exact topic. We also have another event on May 27th where it's titled Solving for the Future. So I think there will also be some conversations about how AI is going to change how we solve optimization problems in the future as well. So
Great.
yeah, for all events, like for all future events, if you would like to sign up, please go to the optimizationforall.com website. I'm going to post it on the chat as well. So feel free to actually like go to the website and look for the sign up link to sign up for those events. So I do realize that we have a 5-minute break.
Yes.
At what time do we come back to the
Maybe
chat?
17, just because I need the extra minute, 3 minutes or 18 now to go over a Timefold. So 18, let's go back.
Okay, yeah.
Perfect. See you.
See you. Yes, we can.
Perfect. I think we can resume our workshop just to be in time. So yeah, just a quick recap of MIP limitations. We have this scalability cliff. At a certain point, the scalability doesn't work anymore and it falls apart. For our case, for example, from X large and beyond. You have this linearization burden. So for your constraints, you have to always think in a linear way. And if they are not linear, you have to linearize them. And when you linearize them, you add this extra complexity, even in terms of sometimes you simplify the constraints too much, like we've seen in S3. And with S4, you add many variables. You add a lot of new types of variables. And if the constraints pile up, that means you will have a very unmanageable model, both in terms of complexity and in terms of number of variables and therefore performance. And when you hit something infeasible, you don't have any actionable output. So that's something that MIP suffers from. So the question that gets asked is, what if we could keep this model and run? Because this is what I love about MIP is because it's a generic or general purpose solver. So you can find it solving scheduling, VRP, design problems, bin packing. So it's very versatile. What if we could keep this paradigm of model and run, but at the same time solve these issues of or limitations that MIP has? And that's where metaheuristics come into place. So it's not a magical solution as you expect. Metaheuristics have been here since the 70s, and they've been a hot topic in operations research since then, basically. But so what these metaheuristics offer is first, so the two approaches are different. So MIP builds the complete mathematical model, hands it to the solver, and then it waits for the optimality. And in some sense, sometimes you would consider this to be a black box, because if you need a PhD to understand what happens behind the hood, I would say that's a black box. So it has this all or nothing paradigm. You either get, it's not either optimality, but either feasibility with some gap or nothing useful. And if it's infeasible, you don't get something useful. Metaheuristics are different. They start with an initial solution, sometimes with a swarm of solutions or a population. But with local search, for example, they start with an initial solution built with some construction heuristic. And then they move on with that solution, they improve it iteratively. This is the case for local search. And they return the best solution found so far. So during that local search loop, during the search, you can stop the search anytime you want. So you can leave it to search for 1 hour, for 2 hours, for 30 seconds, whatever you want. And anytime you stop it, you get something. So you either get a solution that is complete, you either get it incomplete, sometimes it breaks some hard constraints, but you get something. And this is called the anytime behavior. So this is something that's really appreciated for metaheuristics. One limitation though, it doesn't have any mathematical proof of the gap unless you do some techniques and you combine it with MIP or combine it with some clever way of computing lower bounds. But the general framework, you don't have this gap and this optimality proof, and it's not a complete algorithm like people in OR say. So in practice, what does local search have? It has these moves that you apply to your current solution. So for example, in our nurse rostering problem, I can swap between two nurses. I can move one shift from one nurse to another. I can swap between two shifts of two different nurses. And these are what we call moves. Acceptance is when do I accept a move and when I don't. So generally you accept it if it improves the score, but you can also accept it even if it doesn't improve the score. This is done to escape local optimas. And most of these metaheuristic have some mechanism to escape local optimals, because that's one of the challenges of metaheuristics, is because sometimes they get stuck in a place where they don't improve anymore, and it's not a global optimal, it's a local optimal, and they don't know because they don't have this gap built into them, this proof of optimality. But the problem with metaheuristics is this. So historically, they've been painful to implement. So if you had a course of operations research and you implemented metaheuristics, you probably implemented it from scratch. You dealt with move generation, neighborhood structures, how to compute the score. And then you realize that if you compute the score every time you do the move, it's pretty slow. So you move into this incremental updates. How do you get them right? Just one index to the left and everything is off. Because they are these complex algorithms, they have a lot of decisions inside them. So for example, in simulated annealing, the temperatures decide how much worse solutions you accept. How do I set these temperatures, and how many generations do I do? How many looping do I do? All of these parameters influence the performance of the metaheuristic, and you either need to be an expert in tuning, or and this is an open-ended question also, how to tune these parameters. So this is also another problem. And again, they are hard to maintain because they have a lot of components into them, and a lot of these things are repeated, so the moves and everything. And the question is, what if a framework handled all of this automatically? So what if I could have a model and run, but behind the hood, I have a metaheuristic working and a local search working. So in that sense, I will have the same paradigm, model and run, but I wouldn't have these issues over here. So the scalability is better, memory footprint is better because I only explore one solution and with some artifacts that you need to keep, of course. So what if I had that? And that's where Timefold comes in. Timefold offers this, so it's a model and run, but behind the hood, it uses metaheuristics, and it uses local search to be exact. So they don't use other population-based algorithm like swarm optimization or genetic algorithms or something. What's good about it is open source, Apache 2.0, so free to use even for commercial use. Native APIs in Java and Kotlin. They don't have C++ or Python. They had Python, but they discontinued it because of performance issues, and they are focused on more on Java part. So that's that. And they have this model and run paradigm. So they are generic enough to allow multiple use cases to be modeled. And under the search, they use metaheuristics. So they have construction heuristics to build the initial solution. Then local search algorithms that are implemented by default. You don't have to implement them. And they have incremental score calculation. That's really one of the main components why it's really fast and it can work under pressure. So the architecture of Timefold goes as follow. First, you have whatever is in green here, it's what you do. So you define these two components, main ones, the domain, which models the entities, variables, and facts of your problem. And then you define the constraints, just like we've done in MIP. But this time you don't have the linearity constraint. You can model pretty much any constraints you want, even if it's not linear. And what the Timefold ensures is the construction heuristic. They will build an initial solution for you, the local search, but also they ensure the incremental score calculation. So from these constraints, they ensure that the score is calculated in an incremental way, so they don't recompute everything from scratch, and that's what makes it really, really fast. They select the moves for you, and even the moves are implemented. There are some moves implemented by default that the solver just uses. And what's good also is that all of these components can be customized. So you can give them your construction heuristics and keep the rest. You can change the algorithm and its parameters. You can change the moves. You can implement some custom moves. You can change the score, so hard, soft, and you can also have some other levels. And basically, the solver iterates until you stop it or until it reaches a time limit or a limit. And yeah, so during this loop of solving, you can stop it anytime, and it will give you the best solution found so far. So it has this anytime behavior. Okay, so what are the building blocks? Basically, you have this planning entity. So the planning entity is objects that has the planning variable inside of it. So Timefold is built by developers. So it's really developer oriented and it's object oriented even. So planning entities are these objects that contain a planning variable. And the planning variable is something that the solver decides on. It's same as decision variables in MIPS. So for our problem, we have shift assignment, which is an object that holds both the shift and the nurse that works that shift. And the nurse in this case is the decision variable, so it can change during solve time. So this is the planning variable here in the nurse. Problem facts are something just data, so things that doesn't change, and in MIP we call those parameters. For example, the nurse doesn't change; it's just data, and yeah, the nurse. Also, I think that's more of a plain solution. Constraints, you can define this constraint provider, and we will see their API how to do that. The score is what keeps track of the quality of the solution. So we have the most used one is this hard soft score. So it will give you how many hard violations are in the solution and how many soft violations are in the solution. And you notice already the difference because MIP only gives you the soft score because it only works in the feasible region. And it will give you solutions that are feasible, and then it will give you their objective. But since Timefold also can deal with unfeasible solutions, it will give you solutions that have hard score sometimes in them if you stop the search really early on, or if your problem is not solvable, so you cannot solve that instance. And the solver object, which is something that defines the pipeline I showed you here. So the local search, what's the construction heuristics, what are the moves, all of that. This is what the solver factory thing is what manages all of that. So let's try to model our problem here. So first of all, what you would notice is that we don't have math here. It's closer to programming, closer even to business rules. So if you give this code to a business person, they can understand it because it's plain English. So first of all, I have the nurse. This is a problem fact because all of these facts are already defined. They don't change, so the nurse doesn't change qualifications, at least during the solve. So this is a problem fact. And then I define my problem, my planning entity. So the planning entity is this shift assignment class. It has an ID, annotated with planning ID, and it has the nurse. So the nurse is the planning variable over here. So the planning variable is the thing that changes during the solve. So the solver will assign a different nurse every time. It will make some moves to put nurses in different assignments, and that's the field that gets changed in this class. Another thing that you need to define is the planning solution. So it's a container, it's a big hub that has all of these components stitched together into one place. So it has the problem facts. I here have a list of nurses, my list of nurses with their qualification, preferences, everything. It has the list of planning entities. So what are the assignments or what are the shifts that I need to assign or to fill in? And it has a score. So this is the score that the solver keeps track of with the hard soft score. So again, this reads like business code, and even domain experts can read this and understand it. Maybe we have some questions.
Yes, there is a question about what is the limitation of the Timefold?
I will answer that at the end. I prefer to finish the presentation first. So we have this constraint streams API. So this is the way to express our constraints. So it's done in just like Java streams or just like SQL. It's a syntax or framework to express your constraints. So you start by streaming over the planning entities you want, for example, for each shift assignments, for every shift assignment. And then you transform those. So you either filter or join them together or group them by some condition. And then when you express your constraint using these transformations, you penalize or you can also, yeah, so you penalize the violations that you want to measure. You can also reward. So if you want to minimize or maximize things. So this is how the constraints is contributing to the score. And again, these are evaluated incrementally. So every time Timefold finds a new solution, it doesn't compute the score all over again, because imagine you have a very big instance that will take a lot of time, but it will only compute whatever got changed. So if you have 100 nurses and you change only 2 nurses, you only recompute the changes of those 2 nurses and not the whole solution. Okay, let's go for the Codelab. I think we can make it in time. Yes, see you.
Yeah, I think we have 2 general questions. Like,
Yeah.
the first question is, what are the prerequisites of using Timefold? And the second question is there any general method to fine-tune the hard and soft scores?
Okay. The prerequisites for using Timefold, what do you mean? What do you need to install to use it, or what?
I think it might be software prerequisites. What do you need to use Timefold?
You just need to. It's in Java. Here I'm using the Python API, even though the Python API is not it discontinued. They don't support it anymore. But I prefer to use the Python one just because people generally use Python. But generally, if you want to use it in a project, you would need Java or Kotlin, and you would just install the library, and that's it. And you start using it in your Java projects. But if you talk about prerequisites in terms of skills, I think you need some modeling skills because you are still doing modelings. If you model the wrong way, even Timefold cannot solve your problem. So you will need to be very mindful of how you model things in order to not explode the number of variables, not explode the. So in your constraints, you don't want to stitch together multiple entities all over the place. You need to have clean models also in Timefold. But it's just that you don't have the constraints that you have in MIP of linearity and that can make constraints harder to express. So those are the skills for me that you need in Timefold. And of course, programming and all of that. Sometimes we even do internally in our company, we also sometimes do some landscape analysis, because this is still optimization, even if it's heavily in the software and local search. You need an objective function that is easy to go through and not has a lot of spikes. And so we do also landscape analysis, but those are a bit advanced. If you just want to use it on a simple project, you don't need all of that. Any general method to fine-tune hard and soft scores? And I suppose here you mean the hard and soft score, like parameters, and not the scores themselves, if I'm correct. Because, yeah, if you want to do that, generally it's so in real life, let's start by academia. Academia, you can use some design of experiments to do tuning. You can use Taguchi methods. You can use if you are tuning also the metaheuristic parameters, you can use some param ELS and some tuning methods also with that. But if you are solving this in real life, what you generally do is you just offload this problem to the user. Because when you think about it, the soft constraints, they have multiple stakeholders. So nurses, for example, they want the best schedule that doesn't have any lights, that doesn't have any inconvenience, that fits their preferences. But hospital managers, they want schedules that are least expensive. They don't want overtime. They want to reduce the number of people working, all of that. So these are by design, they are conflicting objectives. And what you would do is you would give the possibility to the user to change the parameterization of these objectives. Because at the end of the day, what Timefold does is just a weighted sum of the objectives, that is the objective function. But those parameters are what impact the quality of the solutions that you get. And what you want to do is give it to the user, and then the user, depending on the situation, will play on those parameters. So if in a 1 week nurses are really angry and it's the end of the year, during holidays, all of that, you would give nurses more of what they want. And then if it's something less stressful, you can favor a bit reduce the overtime, reduce the number of people working, all of that. So I hope that answers your question, at least if I understood it. Yeah. Perfect.
Cool. Just for the interest of time, since it's only 41, let's keep the questions to the end and let's go through
Yeah.
the notebook slides. Yeah. Thank you so much.
Yeah. Perfect. All right. So this is again, like I said, I'm installing it from GitHub because they don't even have it in PyP anymore. So you'll have to install it from GitHub. There is this Solver Forge thing. Oh, I think it's already installed. Yeah, it's already installed for me. But you have the other repos that are trying to reproduce Timefold in Python because it's not supported anymore from the Timefold enterprise. So this is just for demo purposes and for this workshop purposes. But the same modeling and the same principles, you just take them and apply them in Java, and that's the same thing. So it's still a valid experience. So here, like I said, you have the nurse, you have the shift assignment, you have the nurse roster, which is the planning solution that, like I said, it has entities, it has score, and it has the problem facts. This is your whole model. This is all you need to solve your problem. So you model this, and then you express constraints. So we will see the same constraints. H1, which was, I think, the number of demand, you don't need it in here because what we've done, we are creating exactly the number of shifts we need. So you will not go above the demand and you will not go below the demand. You will get exactly the number of shifts that you are planning for. Here is just some helper functions to help you enable and disable constraints, just to play with the constraints. So what we have here is the constraint provider, and then in order to express constraints, you do it like this. So You use like I said, the constraint streams API. And the way to do it, for example, here, 1 shift per day. So a nurse can work at most 1 shift per day. What you would say is that for each unique pair of shifts, so what this does, it creates unique pairs of shifts where the nurses are equal. So, and the days are equal. So you are looking for shifts or pairs of shifts that has the same nurse and the same day, and you penalize by 1. Why? Because that means that that nurse is doing 2 shifts per day, and you don't want that. So you penalize by 1, and that's 1 hard. So it's the hard constraints. The second constraint is H3 minimum rest gap. So what you would do, again, here we are just forbidding the 2 transitions from night to morning and from night to afternoon. So what I would do for each shift assignment, and then you can use the filtering. So you filter these, imagine that you have all the list of shifts, and then you filter only the night shifts. You join them with all the shift assignments, so you cross between them, and you only keep the nurses, the shifts that have the same nurse, and have day plus 1 and day. So this day and so today and tomorrow. And if it's one of these, so the second shift, which is B, if it's one of the morning or afternoon, that means I did not respect this rest gap, and I penalize by 1 as well. Qualification match. So for each shift assignment, I filter for shift assignments that have at least a nurse, and then the required qualifications are in the nurse's qualification. So if it's not, I penalize by 1. Unavailability. So for each shift assignment, if it has an assigned nurse, you need to make sure that that nurse is not available. So a.day in nurse unavailable. That means that this day that the shift got assigned the nurse got assigned the shift is not valid. So you penalize by 1. So these are the hard constraints. For the soft ones, so what you would do is this is the shift preference. For each shift assignment, if that shift type that got assigned to the nurse is not her preference, we penalize by 1 soft. For consecutive nights, remember we needed an auxiliary variable for the MIP representation. In Timefold, you don't need any auxiliary variable. So for each shift assignment, if it's night, so you filter only the night shifts, and then you join with the other shift assignments that have the same nurse and have a day equal to tomorrow, so day plus 1, and that are nights as well. If that happens, I will penalize by 1 soft. So you didn't need a new variable. It's just everything gets played in these constraint providers and these constraints that you define. So I set up all my constraints. This is the list of constraints that is enabled. So you can see it here. This is the same generation instance, by the way, and we use seeds from MIP. So it's exactly the same instance that we are solving in MIP and in Timefold. So these are the same instances as before. Small to extra large. And the same visualization method. And then this is how you solve it. This is the solver config. So you have your solution class, your entities, your constraint provider, and then this is the duration. So the termination config, you can stop the solver after a certain number of moves, after a certain time, or after a certain criteria. Maybe as soon as you reach feasibility, you just want to stop. If you reach 0 hard, that's it. In here, we chose to stop after a time limit in seconds. You create that. So this is, you create the solver config, you build your solver, and then you call the solve method. That's it. And the solve method will return a solution for you. And then we have also some helper methods to analyze the score and display the breakdown and everything. Again, this notebook is the same one as the one we sent. We have some exercises that was in the first one that are solved in this one. So I will update the one we shared with the solution to the exercises. Okay, we built our solver, we built our model, sorry, and we built our constraints. Let's try to solve a model here. The first thing that you notice is that, remember when we solved the small instance with MIP, it only took 0.08 seconds, I think. And it solved it to optimality. In Timefold, since we don't have the proof of optimality, we do reach the solution really fast, so in less than a second. But Timefold doesn't stop because it doesn't know that that's the optimal solution. It will only stop based on the criteria you gave it, and for us it was the time. But the objective in let me just open again the MIP one, just to see what was the objective. I think it was for the same. Yeah, so the objective is 4 here. It was S1 preference penalty. And here it's the same, it's 4. So we did find the optimal solution, but we didn't stop because we don't know it's the optimal one. And then if you visualize the schedule, you can see it here, just like the other one, and it has the same issues as before. These two nurses doing all the night shifts, or these 3 nurses doing all the night shifts. So one thing that you need to understand about the score in Timefold is that it has this lexicographical order. What does it mean? It means that just one hard violation of the score is worse than any violation of the soft score. So if you compare score A and score B, score A is -1 hard and 0 soft. It's worse than 0 hard and -90, 90, 90, 90, 9999 soft. Because one hard violation is bigger than any soft violation. And this is what we want, because if you have a schedule that doesn't respect one physical law, it's invalid, even if it has the best soft quality ever. And here between softs, of course, -5 soft is worse than -3 soft. You want to go towards 0. And 0 hard, 0 soft, it's optimal, so we cannot optimize anymore. Let's check the scores now. So this is we have shift preference. Some nurses are preferring types of shift, but they are not getting what they want. Let's see now what happens if we do the same test as MIP and give it something infeasible. So I'm creating the same problem with some inflated demand. Let's see what happens when you solve it with Timefold. So again, with MIP, just a reminder, it says infeasible, and then it's up to you to understand why it's infeasible. Did I make a data input problem? If your problem is very big, that's a really big issue. If you have 2 months of scheduling and tens of people to schedule, and you cannot find the reason easily. But with Timefold, it gives you something. So it gives you something that breaks the hard constraints. Of course, you cannot use this in production, but at least you understand, maybe you get a hint of why this is happening. So in here, we have one unavailability that was broken and 1 shift per day broken 2 times. So that hints me towards saying that maybe I don't have enough people to cover this, because I'm not respecting their unavailability times, and I'm giving some nurses twice the work they should have. And one easy fix is maybe I will get I will hire a new nurse that will take this load, these same shifts that broke the solution. I will assign them to an extra nurse, and then that's it. I got my solution. Or maybe if I don't have these H2 violations, I only have unavailability. I can call my nurse that was unavailable and negotiate with her. Hey, you are unavailable for just one day. Can you work this day? And we will make it up for you next week or something like that. So you have something to work with as a planner. Remember, this software that you are building is not for you. It's for a planner that will be in contact with his employees, that will use this tool as a decision tool, and not as a fancy tool that gives you a gap or optimality and all of that. It's something that will help some person decide on people's lives and people's work schedules. So you need it to be something that is robust, that can work on under any circumstance. So even if a solution doesn't exist, I want it to be helpful, as helpful to the planner as possible. And this is what we have here. So this is the difference, like I said. And here I'm trying with 2 times the demand. You can see also you have more hard score violations, and yeah, you can do something about that. One very good use case of LLMs here is that you can stitch this, so score that Timefold gives you, and give it to an LLM, and it will check these scores and will notice a pattern that unavailability is not respected. So maybe people are choosing some random unavailabilities that make our lives much difficult, and we have to negotiate better with them when they are doing unavailabilities. And these patterns are LLMs can detect them, and this is also one good use case of LLMs with it's not just to solve or model, but to interpret the logs of the solver and the outputs of the solver. Okay, what did you notice about the night shifts? Clearly here the night shifts are not fairly distributed. These 3 nurses are doing pretty much all the night shifts. So let's do our fairness distribution constraint. Here I'm defining a new constraint. So this constraint will ensure fairness in our distribution. So for each shift assignment that are nights and that are assigned, I group them by the nurse and count the number of these shifts. So this will give me tuples, or in this case, couples of nurse and another number, which is the number of night shifts that this nurse did. And what I can do is penalize with one soft this, which is the variance. So you notice that this time I can express the variances with the absolute value and also this quadratic formula. I can express it without issues because I don't have the constraint of having everything linear as I do with MIP. So this, why I need this, because you need to penalize outliers more than, so if one nurse had just one night more than the average, that's okay, I would penalize it with one soft. But if it had 2 nights more, I will penalize it with 4 and not 1. And then if it has 3, I will penalize it with 9. So the score is quadratic, and this means that you will penalize people who have a lot more than the average, more than before. And that was the issue then with MIP, because it penalizes any difference the same amount. So if it's 2 or 5, it's still the same, it's linear. But in fairness, you need mostly you need this quadratic formula to express the fairness in a nice way. So this is these are the constraints now. No, I have to run this first. Yeah, I have this. If I have this nice utility function that compares between two schedules, I will not run cells anymore because that take time. It takes 30 seconds every time. I will just show you the results from now on. Maybe we can have 10 or 15 minutes extra at the end just to finish the notebook, and then we can be. So if you compare it before, which is the unfair one without the S3, and the fair one, here we had these people doing all the work of the night shifts, but now the night shifts are distributed all over the nurses. So you have here this nurse doing either one or two shifts. One problem though is that this nurse is doing 0, and if you dig deeper into the score breakdown, you will notice that the fair night distribution, it's only catching nine nurses here in the matches. And the reason why is that this nurse is not included in our constraint stream. And in order to fix that, you just need to uncomment this line here. So this complement with nurse, so it complements our feed with nurses that have 0 night shifts, because we want to penalize those as well. So if you do it again, and I will just run it and move on, and then we can go back to it. I advise you really to go through the documentation, because there are better ways to deal with the fairness in Timefold. It's called load balance. And I put the link here, which is better than how we are doing it. This is just a way of doing it. Let's do S4. S4 the same, so it uses the two list thing. So for each shift, filter with the nurse. This means that it has a nurse assigned to it. And for every nurse, I want all the list of shifts. And then this custom function here will compute if any shift type gets more than 50%, and it will penalize it. So if you go back just to this one, you will notice that this third nurse that had 0 night shifts now has one, and this one that doesn't have anyone, it gets caught here in the matches. So we have 10 matches instead of 9. Okay. I think I'm going a bit fast, but yeah, because we don't have much time left. This one is the S4. It ensures that you have diversity in your schedule. So if you compare S3 only with S3 plus S4, you will notice, for example, this first nurse only has mornings in her schedule. So it has a lot of mornings. But in the right, you have more diversified work schedule. So you have morning, night, and afternoon. Same here, we have a lot of afternoons, but when adding the constraint, it has a more diverse work schedule. I also have this experiment with time limits. So the more time you give a metaheuristic, the better result you will get, generally speaking. And you can experiment this with Timefold. So you give it different time limits, 30 seconds until 300 seconds. And you can see this for this large instance we are solving, the score gets better over time. So if you give it 30 seconds, sometimes you don't even get the feasible solution. You get -1 hard score. And then if you give it more, the score keeps on improving. So the more time you give it, the better score you will have. So there's one decision I made, which is to not compare the performance, because it wasn't fair to compare MIP with Timefold. One, because I'm using this Python one, which do a translation with the Java version of Timefold, and you lose a lot of performance there. And also this one is an old version from October or something, and the Timefold team always updates the library with more performant ones. So yeah, this is why I'm not doing a comparison between them. But you can see that also what you can see is that it can solve the XL and X2XL instances, whereas the MIP one cannot, and I will show it at the end. But this cell in particular takes a lot of time because it runs all the instances. So do it in Colab or something, or locally, and you will see the summary of all your all the runs. So I gave you some exercises. I'm not sure if anyone did the exercises, but I have the solution here. If anyone did and wants to share the solution, that would be great. If not, I can just show you.
Yeah, I think considering the time, we might need to go through this pretty quickly. I mean,
Okay.
yeah.
Just close this. Okay, so we had this maximum shifts per day. In the exercise, it was maximum 5 shifts per day, but I made it maximum n shifts per day. And you can change this n here, 3, 4, 5, or just to see the impact of this constraint. Because I think if you check the schedules, we don't have more than 5 anyways in most nurses, so you wouldn't see the impact of this constraint. But what you would need to do is group by the week. So you group by each nurse and week. And in order to get the week, you can just divide the day over 7. So this is arithmetic division, just to get the week number out of the day. And in that sense, you will count the number of shifts per week, and whatever goes through over the max shifts, you penalize that. And if you try to do that, you will see that here, I think I did it with 4. You will see that most nurses don't have more than 4 shifts. I will leave this for you. This one will be shared. I see recovery time. I have it here. So the notebook that I will be sharing later will have all the corrections with you. But this one I wanted to test a bigger instance. This is the medium instance, and you can see that it has all the constraints. It has a nice distribution of night shifts. You can see it all over the nurses, and there's a bit of diversity in terms of shift types also when it comes to nurses. So that's really good. Same here. You can see also that the scaling of the number of variables is really nice with Timefold because you only have what you need. Because, for example, here it's just the number of shifts that gets into the size of the model. But for MIP, it's not just that. It's also the number of days, the number of nurses, the number of shifts. But if you need other constraints, we added some variable types, so you have to factor in those into the model size as well. But for Timefold, it's just the number of shifts because that's what you are deciding on, and that's what makes it also really memory efficient. Okay, let's go back to the slides. Here I have just a quick explanation on why Timefold is fast. So they have this incremental score calculation. So what happens is that Timefold does all of these kinds of moves. So if it's entity A, B here, and you move one entity from one slot to another. So the naive recalculation is recalculating for every entity, for every constraint, you recalculate everything. So if you have 4 entities for constraints, that's 16 evaluations. And then 300 entities, 10 constraints, 3,000, and you are doing millions of moves. So that's billions of evaluation that are wasted because not all of these constraints and not all of these entities are concerned with this move. So in Timefold, they do incremental calculations. So that means that you only do calculations on the constraints you touched and only on the entities you touched. So that only 6 and only 20 compared to 3,000. So if you factor in the number of moves, that's why it's really fast. Okay, so just a summary, what Timefold offers you some nice domain modeling that is really close to the business. Constraints as business rules, so you can read them in English because they have this nice constraint streams. You can analyze the score to check what are the constraints that got broke, especially in terms of invisibility. When you have infeasibility, you have this graceful infeasibility, so you will get a solution nevertheless. Easy extension. So if the client calls every week and tells you to add a constraint, generally it's not a big problem. Of course, you need some effort in modeling, and sometimes your model can change a little bit, but it's not as dramatic as MIP. And also scaling. Metaheuristics thrive in scale when you have bigger and larger instances, and that's the case for Timefold as well. So the big question is when to use what. So what you have to know is that they are not enemies. So I'm not saying MIP is the worst thing, and I'm not saying Timefold is the best thing. MIP shines really when instances are small to medium, when you need a proof of optimality, and when you also need optimality, when that extra 2% is really important for your business, you would use MIP. So for financial optimization, for demand optimization, all of that, you would need MIP because just 1% of improvement, that's a really big difference. Also, in that case, you would use it also when constraints are naturally linear and the model is stable. You don't change it a lot. Timefold shines when you have large and very large instances. Constraints evolve frequently, so you have a product that you are developing and constraints are added all the time. When they are hard to linearize and when anytime behavior matters, so you want solutions at any time. And you encounter infeasible instances, either because you have over-constrained models or sometimes because of data inputs, errors or something. And developer velocity matters. So you need to ship quickly features. So for me, they are tools for different situations, and some teams use both. We use both in some projects, and they are both tools for different needs. So time to wrap up. Some advanced features worth mentioning is the justification API. You can justify every constraint violation. They offer also REST API with Quarkus or Spring Boot, so you can just offer your solver as a REST API. Real-time replanning. So if something changes, there are some features to allow replanning. You can define your custom moves. So if you're in academia and have custom moves that are really working really good for VRP, for scheduling, you can use those. They have benchmarking, so you can choose the best algorithm, the best moves. And in their enterprise edition, they have multi-threaded solving also, so you can solve across multi-threads. So the conclusion is MIP is very powerful tool, but it has some limitations that I shared with you. For me, Timefold covers a lot of those limitations, and the trade-off is explicit because Timefold cannot prove optimality, and that sometimes is a go, no-go for some people. Domain modeling changes everything, so especially for developers. If you are writing shift assignment, it's completely different than X and SD, and sometimes it makes the modeling easier. And they are not enemies. You can use both at the same time, and you can use each for a different purpose. Okay, these are the resources. You can visit Timefold documentation. We have blogs about Timefold always, about optimization in general, about business also. Timefold Quick Start is a really good place to start with. And all the materials, I think we sent most of them, but I will send the completed notebook later on. Thank you very much. And if you have some questions, I'm happy to answer them.
Awesome. Okay, so we have 3 minutes. Let's put it that way. we have gone over time. So if you have any questions, feel free to raise your hand and ask, or you could also put it on chat as well. There is one question which actually is getting a lot of replies from the audience as well.
Yes.
Is there a chance the algorithms get stuck in local optima, in brackets, non-convex and feasible space? Or is this addressed internally by Timefold's built-in methods?
Yeah, of course. So this is a problem of metaheuristics in general. They all can get stuck in local optimas, and it's up to you to at least make sure not to using some of the configuration, the time limit configuration or the termination configuration. They have this diminished returns that you can configure, and basically what it says is that when the solver stops from giving substantial changes in the objective function, the solver stops. So if the rate of improvement gets plateaued, the solver stops. This is one useful termination configuration. But you can use time, you can use the score. This is also possible. But the solvers are the algorithms behind the hood, you can customize them there as well. So if you notice that the solver gets stuck a lot in local optimas, you can change the parameters of, for example, simulated annealing or taboo search or late acceptance, because those are the parameters that you can play with to escape local optimas. And you can also play with the moves. So you can have some moves that completely destroy the solution or destroy partially the solution to escape to another region. So this is why Timefold is really good, because you can customize all of these components. So you can choose to keep everything as default and be lazy and implement just the constraints, but you can also customize everything, the algorithm, the moves, the acceptance criteria, all of those. I'm not sure if I answered that.
You got a thumbs up, so I guess you did. So I think we shall end the session there. There's been a lot of like really good comments from people on chat, and a lot of people actually like really liked the presentation. I mean, so thank you so much for actually like spending time with us and teaching us about the differences between MIP and Timefold, and what are the modeling criteria to actually make things a lot more quicker and a lot more solvable as well.
Yeah.
So just to reiterate, we will be sending everyone the slides again, and also we'll be sending the solution, the notebook as well. So Amin will share with us the link, and we'll
Yeah.
also share with the community as well. But apart from that, feel free to actually go to optimizationforall.com to actually like go through like future events. Oh, Ha, do you have something to say? Oh, sorry, you're muted, Ha.
There was also a question from Ahmed. There is some response, but I'm not sure if we also want it to be addressed by Amin. I'm not sure. And I still see him in the meeting, so I'm not sure Ahmed is.
Okay.
Yeah, I had a very quick question, but I think the time is out anyway. It's about constraint programming. So I was expecting a comparison between mill constraint programming and Timefold. So I was just waiting for that.
Yeah. So I was going to add CP to the mix as well, but for time constraints I couldn't. But you can contact me so we can discuss it. You can contact me on LinkedIn or send your question, because I also worked with CP and I have some opinions about where it sits between these solvers. But the short answer is that CP is really good when it comes to expressing constraints that are naturally not linear. CP Optimizer, for example, handles really well scheduling because it has these interval variables into place. It also is a complete algorithm, so it offers the optimality gap and all of that. And it offers a lot of performance when it comes to feasibility. But when it comes to optimization, I think it falls behind a little bit MIP, and I would be really interested to compare it with Timefold. But also the best constraints programming solvers are also not free. So CP Optimizer is not free. Higgs-Ali, I think, uses some of these techniques also, and it's not free. So that's also something that needs to be addressed when you talk about CP, because our tool CP, I don't think it's that performant when it compared to MIP and Timefold.
Thank you very much. Thank you.
answers a bit. Yeah.
All right, cool. As I said, feel free to actually visit our website optimizationforall.com for future events. And yeah, thank you so much for joining us. Thank you again. I mean, really appreciate your time.
Thank you very much. See you
So-
next time.